she will try. If she is fine with it, we will take it. If it's not, she will use it and we will run.
Yeah, it's okay. We'll do it as we can. Yeah. What is this? This is the translate?
So should I leave this one
Wow,
here?
we are.
Oh, sorry. I'm just going to use the.
So you will give it to the inspector, this one? Yes? Oh, she will speak with this.
So how to? Ah, good.
Yeah.
Oui, tu peux le présenter. Mais il fallait garder, il y en avait deux. Dedans. Il fallait garder le un, mais pas le deuxième. Parce que si tu gardes le deux, ça tombe. Non, mais c'est super.
Ah non, j'ai compris qu'il fallait l'enlever. Parce que c'était pas important. Please, of course. We will need more glasses for it. des gens.
So, good morning, everyone. Let's start the session. We are starting part 2 of the conference, actually. The last few days we had part 1, which was already quite intense. We had several hundreds of presentations in the parallel sessions, and every day we had well-attended social and outreach events. So I hope everyone still has a bit of energy left to embark on the second part, which is the plenary talks during the next few days. Before we proceed actually to the EPS prize ceremony, I would like to introduce a few special guests that we have among us. First of all, well, both of them are strong women in charge, so I think this university is making real efforts in terms of diversity. So first of all, we have Isabelle van Driessen, professor in chemistry, and she's the current dean of the Faculty of Science since a bit less than a year. I know that she is supporting all kinds of science-related events, and that she is doing special effort also in science communication and outreach, so it's a pleasure to have her here among us in this session. Next is Mieke van Herwegen. She is our current vice rector since about 2 years. And actually, I would like to invite Mieke to say a few welcome words before we proceed with the prize ceremony. So.
This will be okay. Morning, everybody. Mrs. Dean, distinguished guests, dear organizers, dear colleagues, dear delegates. As Vice Rector, I would like to welcome you all warmly to Ghent and to our university. It's a little bit strange to do that in the middle of a conference, but that's the way in which it's organized here, so that's the way I'm going to do it. It's a real pleasure, I have to say, to see such a large attendance at this major international conference. The fact that the High Energy and Particle Physics Division of the European Physical Society has chosen Ghent as location for their event is obviously a great honor to all of us here at Ghent University. Just to give you a little bit of history, because you've been walking around the city here for a couple of days now, and I don't know how much you know about Ghent and about its university, so let me give you a little bit of history. History of Ghent actually started in the year 625, so in the early 7th century, when St. Amandus chose the site of the confluence of the two rivers, the Lys, the Leie, and the Schelde, to construct an abbey. And nearly 1,400 years of history are still really visible in the historical heart of the city today. We have a medieval castle surrounded by a moat. We have an imposing cathedral, we have a belfry, etc. I hope you will have found some time, or you will find some time, to visit some of these in the week that you're here. In the 13th century, actually, Ghent was the second biggest city in Northwest Europe after Paris. You wouldn't say it today, but then we were the second biggest city. Today we're a bit smaller, but still, now is a quiet time because it's a holiday time for the students, but we normally have approximately 70,000 tertiary students around here, tertiary education students around here in Ghent. And Ghent has a population of about 250,000, so the students have a vast impact on the population in Ghent and on its social and cultural life. Ghent University recently celebrated its 200th anniversary. Our university was founded in 1817 under the rule of King William I, who was then King of the Netherlands. At that point, here, the region here, was part of the Netherlands. We were not Belgium yet. In 1830, we became Belgium, and then things changed a little bit. But in the early days, like in the northern Netherlands, the southern Netherlands, that's what we were called at the time, received 3 state universities. One in Leuven, which was a continuation of the existing university there, one in Liège, and ours in Ghent. So 3 universities erected in 1817. And in that first year, our university had 190 students. That's only about, I don't know, a fifth of the people that are here. 13 staff members and 16 professors. Can you imagine living in a world like that? And of these 16 professors, 9 actually came from abroad, mainly from the northern Netherlands and from Germany. We started with 4 faculties: arts, law, medicine, and the Faculty of Science. The official language of the university was Latin. Yeah? Fortunately, things have changed since then. Now, after the Belgian Revolution in 1830, our university was subjected to a number of important changes. French became the official language, also the language of tuition, language of education, and the university lost its faculties of arts and also of science for a couple of years, but they were returned soon afterwards. The university's reaction actually was to launch the so-called free faculties, where professors were teaching just for free. They weren't paid. But fortunately, as I said, that was only the case for a couple of years. Now, towards the end of the 19th century, new laws on higher education required the universities to conduct scientific research, because in the beginning they were teaching universities. Towards the end of the 19th century, we became a so-called Humboldt University, where research was also extremely important. And that was an important stimulus for research at Ghent University. It was also in the same period, in 1882, that the first female student, Sidonie Verhulst, entered our universities to study science. Unfortunately, she didn't graduate, but she did study here for a couple of years. I think she didn't graduate because it was too difficult for her in this completely male environment. In 1930, the university in Ghent became the very first university in Belgium to teach through Dutch, so from Latin to French to Dutch. The fact that the language of education has changed a few times over the years is emblematic of this very complex linguistic situation that we have in Belgium. And that actually is the main reason why the number of courses taught through English at our university is still relatively low. We still have this fairly complex linguistic situation here. State University of Ghent officially became Ghent University in 1991 and was finally given a considerable degree of autonomy. Now, today, the university consists of 86 academic departments spread across 11 faculties. Next to Ghent, our university also has campuses in Kortrijk, in Bruges and Ostend. And since 2014, we have a global campus, what we call a global campus, in Incheon, near Seoul, in South Korea, where we also have Ghent University diplomas that are being delivered there. We currently have around 15,000 faculty and staff, and a total of over 44,000 students, of whom about 12% are international. In the international rankings, you know, at these speeches, you also have to say something about rankings, whatever you think about the rankings. But in the international rankings in 2018, Ghent University was ranked 61st in the Shanghai ranking. As first Belgian university, we didn't do as well in the Times Higher Education ranking. There we ranked 143rd. What's maybe interesting to you is that for the past 200 years, Ghent University has had many outstanding members of faculty and alumni, such as Joseph Plateau, who was a physicist and a mathematician and precursor of the cinema. Yeah. We also had Leo Bakeland, who was a chemist, who, among other things, invented what is now called Bakelite. It's a derivative of his name, which is a plastic material that is currently used in the construction of certain particle detectors that used to be, this is how I know it, that used to be used in, for instance, these old dial phones, these old phones that were completely made of Bakelite. And we've also had Dirk Vriemout, the first Belgian astronaut, but there are many others. I can't name all of them. Within the Faculty of Science, you might be interested in that as well, the research and education is organized in 13 departments, covering a wide range of topics in, for instance, chemistry, biology, biotechnology, mathematics, and much more. And there's also the Department of Physics and Astronomy, and its experimental particle physics research group, which is participating in this conference today, well, this week. The organization of the conference and of all of the social and outreach activities that come along with it is a major endeavor and is carried by all the Belgian experimental particle physics groups together, acting as one single team. These are the groups from Ghent University, from the Vrije Universiteit Brussel, from Antwerp University, from the Universite Libre de Bruxelles, and from the Universite Catholique de Louvain. I believe that this conference will surely strengthen even further the international visibility and the close collaboration between these research groups and universities that has already been in existence for a long time. I hope you will be enjoying your stay in Ghent. I wish you all a very productive conference or a continuation of the conference with many fascinating contributions and discussions. Our motto at Ghent University, you may have seen it around, is Dare to Think, meaning that we encourage students and staff members to adopt a critical approach, which I'm sure all of you will be doing in the next few days. Events like this are important to exchange ideas and hence to make progress in science. Therefore, I would like to wish you an inspiring event, but also a delightful stay in our beautiful city of Ghent. Thank you.
Thank you very much for this nice presentation of our university. So now we proceed to the next part, which is the EPS prize ceremony. And this part will be chaired by Barbara Erasmus, the president of the EPS High Energy and Particle Physics Division. So I hand over the floor to Barbara.
Thank you, Michael. On behalf of the High Energy Board, I am really delighted to award this year's prizes and to announce that the High Energy and Particle Physics Prize of the EPS for an outstanding contribution to high energy physics is awarded to the CDF and D0 collaborations for the discovery of the top quark and the detailed measurements of its properties. Both collaborations are represented here by the spokesperson, so I invite the spokesperson, Giorgio Ciarelli, Paul Granis, Dmitry Denisov, to join me.
So on behalf of the D0 collaboration, I would like to thank the European Physical Society for this lovely award, who we very much appreciate. I think it brings a lot of pleasure to a great many people. The number of colleagues in D0 over the years now numbers something like 1,500. And I'm sorry they're not all here to join in this event, but it is a pleasure. A brief history of D0. It started in 1983. We're supposed to complement CDF, which had begun a few years earlier. It emphasized a detector which was based upon very finely segmented liquid argon calorimetry with an excellent muon detector, but unlike most modern collider detectors, no central magnetic field. The Run 1 operation began in 1992. The second of the physics publications was in fact on the subject of the top quark, the last existing lower limit on the mass of the top quark at 131 GeV. And yet in that paper, the picture on the right was a striking event which had very little background against the hypothesis of being a top with very energetic electron, very energetic muon, large missing ET, and 2 jets. The fifth publication of D0 was the paper Observation of the Top Quark in 1995. And then in 1996, Run 1 ended, and at that point, the collaboration had netted 132 publications. There was a substantial upgrade for Run 2, which began in 2001, and at this point, a magnet was added. Tracking detectors were completely rebuilt, upgrades to the muon detectors and the calorimeter, and expanded triggers. And the run began in 2000, as I said, and ended in the end of September 2001, when the Divison shut down shortly after the start of the LHC. And to date, we have 498 publications, with several more in the pipeline to come. So let me turn briefly to the top discovery. These are the figures from that paper. Since D0 had no central magnet and no displaced vertex trigger, it relied very heavily on topological variables, such as aplanarity and HT, the sum of the transverse momentum of the objects in the event. And this slide on the upper right shows the separation of signal and background, quite a considerable separation based on this HT variable. And when taken together with rather stringent cuts, we found 17 events with a background of just under 4, and the background-only hypothesis rejected at 4.6 sigma. So the main plot from the paper on the lower left, showing the signal contribution expected, the background expected, the histogram of the data, and a very clear evidence for an element which had to be attributed to the top. The plot on the right is a two-dimensional plot of the 2 jets and the 3 jets in a top quark event decaying hadronically to W into 2 jets and a B jet. And the background peaks at relatively low values of the 2 jet and 3 jet masses. The top is expected, of course, to peak at 80 and 175 or thereabouts, and the data shows a clear preference, a clear contribution from the top contribution. March 2nd, 1995, the announcement of the discovery of the top quark was made simultaneously by the 2 collaborations. I've always liked this picture for several reasons. First of all, you can't tell which of the 2 speakers is, which of the 2 collaborations is speaking. Secondly, there is not a single laptop or iPhone there. Everybody's looking at the slides instead. And of course, the room was full to overflowing. So 50 inverse picobarns was used for the discovery paper. That ultimately grew to 10 inverse femtobarns. And with that larger data sample, a great many studies of the top quark were done. Measurements of the production of TT bar pairs and also single top. Not only the cross sections, but the polarizations, the spin correlations, forward-backward asymmetries, and searches for resonances of excited tops or TT bar resonances and the like. Many measurements of the top decay, including the branching ratios, the W helicity, and searches for charged Higgs, and many measurements of top quark properties, including the mass, the spin, the charge, and the anomalous couplings of the top to vector bosons. Many of these studies remain competitive in the world today, despite the LHC turning on and being a top factory. And in the next couple of slides, I want to show a few of these comparisons that the top scenario, the top studies are still being contributed from the Tevotron. The first is the top quark mass. One measures the mass often by comparing the distribution of the fitted mass of the component objects to a Monte Carlo. That can be done rather precisely, but we have not a very clear idea what that number means, or at least not a very precise understanding. In this particular case, the D0 precision on the Monte Carlo mass measurement, 0.75 GeV. I took the numbers from the LHC, not from this meeting, but from the last top workshop at the end of 2018. And for comparison, the CMS experiment precision was 0.5 GeV. So the LHC is clearly overtaken, but not by an enormous amount. The more theoretically well-defined pole mass is something that is theoretically interpretable, but is measured less precisely. In the case of D0, we have now done it to within 2.5 GeV, to be compared with 1.7 GeV from the Atlas experiment. One of the highlights of the Tevotron measurement of top properties was the discovery of the single top production by the electroweak interaction. That's a process which has a cross-section which is about half that of TT bar, but fewer objects in the final state, and therefore larger backgrounds that have to be contended with. And so this was really a tour de force for the use of multivariate techniques. In this particular case, there are 3 different processes which can take place: a T-channel exchange of a W, S-channel exchange of a W, or an S-channel exchange of a B quark. For the T-channel process, which is the most dominant, the precision from D0 alone is 16%, to be compared with CMS of 15%. At the LHC, the S-channel process has not yet been definitively observed, whereas it has been seen by the Tevotron experiments. And the B quark S-channel process is seen only at the LHC, so they're complementary in this case. And the single top processes are useful for a variety of studies of often beyond the standard model or sensitive tests of the standard model. For example, the CKM matrix element was recently measured by the combination of the 2 experiments to be 1 within 5%. And finally, the production of top, and here there is clearly enormous difference between what was possible at the Tevotron and what is done now at the LHC. The production of TT bar pairs goes up to close to a 1 TeV at the Tevotron, as shown on the left, and on the right, the Atlas measurement, which now goes well above 2.5 to 3 TeV, plus the observation of the top quark production in association with vector bosons, and more importantly, in association with the Higgs in order to measure the Yukawa coupling. Nevertheless, even in the production, there are important contributions that remain from the top, in particular the forward-backward asymmetry. Since the Tevotron is a collider with protons and antiprotons, that asymmetry is relatively large in the standard model and grows as a function of the mass of the TT bar pair. The LHC, one measures something that is relatively smaller and is still not definitively observed. So in this particular case, the 2 colliders are quite complementary. So let me close by simply recording the thanks and the appreciation that we have for the various technical contributions to the experiments from Fermilab. The accelerator department managed to get a factor of 400 improvement over what they said they would do when the program started out. They very nearly caused the experiments to raise the white flag and to give up with the flood of collisions, but we managed to sustain it. And of course, there has been a tremendous funding from the agencies and all of the collaborating institutions around the world in the collaboration. So in closing, what I'd like to do is to ask all of you in the audience who have worked at one time or another on CDF or D0 to please stand up so that we can all see how the thread has gone. Congratulations to you all.
Can you put up my presentation, please? Okay. So first of all, I would like to thank the EPS for this award. It's a real thank by the whole collaboration that we were surprised, happily surprised, to hear of this award. My presentation is dedicated to the people of CDF who made it possible, to the women and men who made it possible, because it doesn't just come after 25 years from its discovery, 24 years from its discovery, but it's also the product of a long story that made it through. It works. Okay. There is a sobering reminder that several of us are not with us anymore, and we'd like to thank them again to remember for the time being. So the starting point, my presentation is more about the starting point of the whole story. CDF started with this design report. By no means it's a design report, the kind of design report you see today. It is a much thinner object, much more serious, and in just one page is the number of proponents, and you can read their names through. The actual starting point was this one, was October 13, 1985, when first collisions were observed. This was our E-log, because it's a picture. This is a picture of the VTPC reconstructed event, and this is the global signature. Here you can't read, but it says that 3 bubbles were available at CDF. And in fact, left to right, Johnny Elias, Kuni Kondo, Alvin Tolle, Stropro Schwitters, Lee Holloway, and then you can see Sergio Bertolucci, Bill Foster, myself, Steve Hahn on his back. And these 3 flags up here indicates that CDF was started by Japan, US, and Italy. It was a joint project, and this first achievement just let us with a little bit of room for new discovery, because by then, by 85, you remember that at CERN already W and Z had been discovered. So the missing piece was the top quark. We are going after it. It took many years. This was our first hint in CDF. I'd like to share, as Avi Yagil showed in top turns 10, these EMU events, top TT bar pairs decay electronically, both doubles decay electronically into electron and muons and neutrino, so missing energy, 2 neutrinos, a nice jet which happened to be B-tagged. So this was really the top events, but of course the DPF meeting at Fermi was shown without the secondary vertex. It was a long debate, but no way to show it. Then we kept in our pocket. Fast forward, otherwise you will never go through. Coffee break, 1994, the evidence paper. This PRD signed by 34 institutions, by then 5 countries, Canada, Republic of China joined, 1,000 citations. Instead of 1,000 citations, I took a couple of posters from the Top Turns 10, which was a very, very nice reunion in 2005. Evidence for top, this is the role of the silicon vertex detector. These are beautiful events, and this is a bunch of information about the top that was there. So besides 1,000 citations in our area, we gave some food for thoughts to other areas. This is a book by Ken Stanley, a philosopher of science philosopher, and there was a long discussion about what the meaning of observation versus the meaning of evidence is. And I think that one of the most important points was the role of evidence in physics after that. Somebody took notice even outside our field. Big things were happening. Still, Newsweek dedicated 2 pages on how many scientists does it take to screw in a quark. Too many, if you read the paper, the article, for too little, you may wonder. Okay, so then March 2, 1995, a new quark is born. First, you have noticed that in Paul's very nice presentation, there was the date was February 25, 1995. That was when this action came through. These are the 4 people, I will say names in a second, that sent a CDF paper to PRL, left to right, Brian Weiner, Lina Galtieri. She's here. Lina, do you recognize yourself? Richard Hughes, Mel Schocket. You can recognize Mel's sweater. And so this is a reconstructed top mass peak. These are the 4 spokespersons: Giorgio Bellettini, Paul, John Peoples, head of the Fermilab director, Hugh Montgomery, and Bill Carruthers. So the week of differences, because my memory is not faulty, John Peoples was outside in Brazil for some school, and the decision was that besides sending to PRL, it must be made public at Fermilab for the first time. Lina is saying yes, so we're not faulty. Okay, so this time a bunch of journals and newspapers took notice of the events all over the world. We got more than 3,300 citations. With these predecessors, the PRD for evidence, and the 0 counterpart we made with the 50 years PRL best paper. So, what then? Top is a difficult object. We knew that our detector was not enough, was good, but not good enough. So we went forward with a technical design report. So by now, we've become more careful. CDF2 collaboration has grown. It is not just 1 page, there are many more pages. And we had to build this new object. Again, a tracker, calorimeter, an inner tracker, and a silicon microvertex detectors. The stakes were high, and I think that both collaboration did it. This is a compilation by Chris Quigg a few years ago of the situation of the top mass, which is one of its most important properties, of course, as we all know, for its role in the Standard Model. And before the Hadron Collider came in measuring it, and after the measurement. And so even before LHC times, that of course LHC took over, we did our job of measuring its properties in a precise way. One big achievement already mentioned by Paul that I still would like to remember is the electroweak production of single top. This is a CDF paper of the observation, so the list is much longer than before, 61 institutions from 15 countries. I'd like this picture because this picture is a joint CDF and D0 picture. In a sense, single top, we were separated, but separated within the same house, so we worked together to make this observation. Overall, CDF published 51 theses, 133 papers on top properties, measuring essentially all of the possible properties of this strange particle. Paul and I did not agree on which slide we should show, but he didn't show this compilation of top cross-section, which is still striking, 6% accuracy in top cross-section. To do so, we had to use all the deliverable beam from the accelerator division. They did a great job, as you can see, by stored number in terms of luminosity, or if you prefer, by starting point January 1st, 2003, or up to 2011. We became smarter over time. This is a typical CDF shift overnight. One guy sitting, watching the DAQ, one guy somewhere in the world, he's Simone Donati in Italy, and John Yo sitting as a physics coordinator, psycho killer in the control room. So it took 24 hours a day, 7 days a week for many years. So I come to my conclusions with this sharing with you this memory of a very nice recollection of TOP, which was done in the Top Quark Third Stand in 2005. It was a celebration of this achievement. It was internal, if you wish, to the true collaboration, but it was also a reunion. Many of us had not seen each other for many years. Henry Frisch, John Cooper was outside, Aldo Menzione, and of course Alvin and Dihan, two of the pillars of CDF, and Alvin should have been here. And so I'd like to thank you again for this prize, and thank you for your attention.
Thank you very much. To present the Cocconi Prize for an outstanding achievement in astroparticle and cosmology, I ask Mauro Mezzetto, my colleague from the board.
Good morning. The Giuseppe and Vanna Cocconi Prize is intended to award an outstanding contribution to particle astrophysics and cosmology. This year is awarded to the WMAP Planck collaboration for providing high-precision measurements of the cosmic microwave background temperature and polarization isotropies, leading to detailed information on properties of the universe and tests of cosmological models and fundamental physics. For the WMAP Planck collaboration, we ask to come here two representatives, Professor Gary Inshav and Professor Nazareno Mandolesi.
Great. Good morning, everyone, and thank you very much. Is this the laser? Yes. Great. I'm here on behalf of Chuck Bennett, the PI of WMAP, who was not able to be here this morning. And he and I both extend our heartfelt thanks on behalf of the entire team for this award. And I'd just like to spend a few minutes this morning kind of going over what we feel is the legacy of WMAP and the standard model of cosmology. Since this is a particle physics meeting for the most part, and most of you may not be familiar, I'll just spend a few minutes kind of reviewing the standard model and WMAP's role in the contribution to that. Let's see, so the cosmological timeline, this is indicated very schematically in this space-time diagram, if you will, showing the evolution of the universe on the x-axis and time, cosmic time, and the expansion history, or the scale factor, indicating the expansion of the universe over its history. Both in very schematic axes, semi-logarithmic, not at all intended to be accurate, but just representative. And we feel there's strong reasons to believe that that our observable universe was born out of a period of accelerated expansion that we mostly call inflation, and that gave gave rise to the observable volume that we can access today. And then the universe has been expanding and cooling. It started off in a hot, dense phase. There was a plasma epoch for about 380,000 years. The microwave background radiation was released at that point very early in the history of the universe. And the CMB photons have been free streaming across the universe for the next 13.7 billion years or so. And this is the epoch that we observe with the cosmic background radiation with both WMAP and Planck. So this is 15 to 20 years of many people's careers spent measuring this map here, but this is the final full sky map from the WMAP project. This is a full sky, let's see, back. Right. A full sky projection, north galactic pole, south galactic pole, and unwrapped over the full sky. And you can think of this as essentially a baby picture of the universe at age 380,000 years, fairly old baby, and that this represents essentially the final conditions of the early universe, the so-called plasma epoch, when it was hot and dense, and also the initial conditions for the subsequent universe, the seeds for the evolution of, for the formation of galactic structures, and so forth. And encoded in this, because the CMB has largely propagated across the universe unimpeded, is a tremendous fossil relic of these early days. So the map itself just looks like Gaussian, like random noise, and for all intents and purposes, we think that's what it actually is. But there are remarkable features in the map if you analyze the statistics. And you have to do averaging to actually pull out these features. So there's roughly 11,000 or so isolated local maxima in the temperature anisotropy, the red points throughout here. And you can just identify and select all of these points, draw a little postage stamp image around it, and then just average them all together. And what you get is this picture on the upper left, where you have clearly a hot spot in the center because you selected for that, but you also have a cool ring around the outside, and that's a very profound feature of the background fluctuations, that this is interpreted as an acoustic wave front, that you have dark matter, photons, and baryons all initially overdense in a region of space. The photon pressure pushes out on the baryonic gas for 380,000 years, at the speed of sound in this plasma, and then when the photons decouple because the plasma becomes neutral after it cools, this structure is frozen into place, and that's what we observe in the microwave background. You can't see it in the map because you're just randomly superposing all of these points, and so this ring structure gets washed out in the image. But if you average it all together, that's what's there. And that's a very profound statement about the initial conditions that seeded these density fluctuations prior to the plasma epoch. And that's where really most of the power of the CMB to determine cosmological parameters comes from. A more familiar rendition of this is in Fourier space. So if you just Fourier transform this profile and square it, you get the angular power spectrum as a function of multipole moment, which is just the conjugate variable to angular separation on the sky. And this is the Fourier transform of the WMAP map, sensitive out to angular scales of about 1/4 of a degree, which corresponds to multipole moments of about 1,200 or so. And just for comparison, this is the measurements of the power spectrum pre-WMAP, just to indicate the substantial progress that a full sky map with sensitive radiometers is able to deliver. So this is really also the quantity that theorists predict. So this is where you make the contact with the cosmological model. So the standard model of cosmology now is for 20 or so years has been the so-called lambda CDM model. That's the ingredients of that model are a spatially flat universe, possibly come out of the result of a period of inflation, with Gaussian adiabatic initial perturbations, say a little bit more about what those mean, dominated by dark matter, or dark energy lambda and dark matter CDM, so the lambda CDM model. There's 6 parameters that go into describing that cosmological model to describe that angular power spectrum. And the WMAP data was able to reduce the allowable error volume of that 6-dimensional parameter space by almost a factor of 70,000, just going from the initial angular power spectrum to the final one. And lambda, this 6-parameter model survived that tremendous stress test. So that's really quite a remarkable testimony to the theoretical model of the early universe and genuinely how simple the early universe actually is. And of course, we get parameter measurements from that process. And for example, the age of the universe is measured now to better than 1% at 13.77 billion years. The results from Planck, as René will also discuss, are both consistent with and substantially extend the WMAP results. The angular power spectrum from Planck goes out to much higher multipole moments, and there's quite a bit more constraining power. Lambda CDM still survives, just in case you're worried. But that also is a remarkable legacy because it's clearly 2 very independent experiments are measuring the same thing, so we're quite confident that's the genuine CMB fluctuations. What lies ahead for lambda CDM? Well, lambda and CDM, hopefully, we have no idea what either of these components that make up 95% of the universe are. We have some ideas, but we don't have any evidence. It's not at all clear how we're actually going to make progress cracking those nuts, but I hope that the coming decades will be productive in that regard. Just on the context of lambda CDM, there is some interesting tensions and perhaps outright conflicts that are emerging now with the measurements of the Hubble constant, which is the local or the current expansion rate of the universe. There's 2 families of techniques, one which just involves directly measuring the distances to nearby galaxies and asking how fast they're receding away from us. And there's a couple of different ways of doing that, the distance ladder, as it's called, and this newer technique called gravitational lensing time delay. And those are producing numbers that are up around 74 kilometers per second per megaparsec. The predictions from the early universe observations, the CMB and the baryon acoustic oscillation signature in galaxies, comes up with something more like 68. And the error bars on these 2 sets of numbers are now small enough that tension is up around 5 sigma. So it really is starting to look like there's an actual conflict in the cosmology that needs to be resolved, which might require some subtle modification of lambda CDM or a new component, or it's really not at all clear. But it's becoming very hard to pin this on systematic measurement errors because it would require more than one set of systematic errors to explain. So that's an interesting development to watch. And just lastly, on inflation itself and this idea that the universe came out of this period of accelerated expansion, there's a number of kind of generic predictions of inflation, which are not necessarily unique, but there's things that we can at least test. I've listed 5 of them here, and I'm not going to go into detail. Perhaps the Planck folks will. But basically, you need a flat universe that if there was any primordial curvature, inflation would have diluted it to an unobservably small level. We observe that the universe is consistent with flat to within our measurement errors, with now about 0.5% with Planck. They should be Gaussian distributed, so the PDF for the temperature fluctuations in the map should be Gaussian. That's consistently observed. They should be adiabatic, which in this case means that the different species were perturbed together at the end of inflation, dark matter, baryons, and photons, and that gives rise to the coherence of this BAO feature that we observe. And right now, there's only upper limits on additional components that might admix with the adiabatic component. And then finally, the spectrum of primordial fluctuations, so how much RMS fluctuation there is on very large scales compared to very small scales, generically is expected to be scale invariant, so those should be kind of equal on all physical scales. But inflations, the simplest models of inflation predict a slight tilt in the spectrum where the small scales have a little bit less power than the large scales. That's now observed in this parameter called n sub s, the scalar spectral index, that a scale invariant value is 1. We observe it to be a little bit less than 1 at almost 5 sigma with WMAP, and I believe more than that now with Planck. So all of these tests of inflation stand up to all of the CMB measurements now. The smoking gun test looking ahead is the search for the so-called B-mode polarization in the CMB. If inflation occurred at a high enough energy scale, it should leave behind a relic abundance of gravitational radiation in the universe. That imprints a particular signature on the CMB polarization that people are now anxiously looking for. And so there we may have significant news on that in the coming decade as well, but still that's kind of the remaining test that inflation needs to really rise to the level of physical theory as opposed to an idea, I think. So hopefully that will be quite something to look forward to. And I'll just leave it at that and just say thank you on behalf of the entire team. We're a small team. We're about 30 people. I don't think there's anybody from the WMAP team here today aside from myself, but I and Chuck and the rest of the team extend our heartfelt thanks and appreciate it.
Does it work? Okay. Thank you very much for this prize. I'm honored on behalf of the entire Planck team to receive it. Here I don't think there are many Planck people, but certainly there is one, François Boucher, which I've seen before. But if there are, yes, there is one, at least François. So, this is what I need. Thank you. If Gary, if we didn't talk since this morning, and my talk is a carbon copy of yours, so something of this kind. So let me go ahead and look at the number of institutions involved in Planck. 100 of institutions. At the peak of the activity, there were more than 1,000 people involved, including the industry, the private industry people. So there are commonalities with the high energy physics and the CMB cosmology, and certainly it's the number of people involved in the experiments. Probably WMAP is an exception. But the time for making an experiment arriving to the results, it's as long as the high energy physics one. So there is these commonalities, but first of all, the most interesting commonality is the fundamental physics. After all, CMB cosmology looks back to energies of the universe when the energies involved were of the order of 10 to the 19 GeV, so which is unbelievable. If we proceed in this research, at some point we will get. So this is another way of showing in a single shot the universe which we see. Starting from the first light when the CMB was emitted, the cosmic dark age at something like 1 million years after the Big Bang, the bright galaxies form, and then big galaxies, and today. So that's an easier version of what Gary has shown. As I said, the commonality with your community here is the time. We started in 1992. The launch was in 2009, and we are still delivering the last papers. Probably there is one left. So it's still to be finished. 27 years. So if you want to dedicate 27 years of your life to a space mission, this is the kind of mission you have to deal with. With respect to, yes, sorry, let me go back. With respect to WMAP, they were first, but we did more. I wouldn't say better, this is something, but we did more, much more. So, apart from that, what we observe after we get rid of the monopole, which is the CMB 2.7 Kelvin, and the dipole, the maps that we observe with two instruments, in temperature are here, represented from 30 gigahertz to 857 gigahertz, and in polarization. This is what we did more than with respect to WMAP, apart from the resolution and the number of frequencies. You see that the dominant part of those maps are the galaxy. And the galaxy gets smaller and smaller here at frequencies of the order of 70 to 100 gigahertz, where the synchrotron and the free stops to be dominant and the dust starts to be dominant. So in terms of, we have to clean those maps before arriving. We have to get rid of the galaxy and other foregrounds in order to arrive to the CMB map, anisotropy map in temperature. And you can see here what the situation. This is the signal of the CMB. Antenna temperature is not steady because it's an antenna temperature. And you see the contribution of the synchrotron, the spinning dust, the free, the thermal dust, and the order of magnitude of the temperature is a few tenths of microkelvin. When you go to polarization, the situation gets much more critical in the sense that the signal we have to deal with is of the order of a few microkelvin, and the dominant foregrounds are the synchrotron and the thermal dust. So, doing this, we get the temperature map. That's the last one. We delivered 3 times the same map in 13, 15, and 18. And all the 3 maps analyzed in different waves with different chunk of data are the same, absolutely the same. No difference from one delivery to the other. So the stability of the temperature CMB map is huge. In polarization, instead, this is the first full map which we were able to produce. Here there are 2 components, one which goes like the gradient, and it's called polarization E, and the other which goes like a curl, and that's the reason why it's called the bipolarization. Everybody's looking for the bipolarization because it means to discover primordial gravitational waves. So up to now, no one has detected, if not a false detection, though over a few years ago. A better resolution of the map, you can see 20 arcminutes by 20 arcminutes. So huge improvement. And what Planck did was the detection of the lensing. The lensing, due to the curvature of the universe, the curvature of the space-time, due to the dark matter, and the dark matter curve the space-time, and you see the lensing effect here. And this is the first map of the lensing seen for the first time. It's beautiful. So going to the power angular spectrum, you see there that this is the way to analyze the map. It's a two-point correlation function, and you see the peaks there, and with Planck we arrive to the first, second, third, fourth, to the seventh peak, I guess. And the points are the measurements, and the blue line is not the fit, is the model. So it's amazing how well the measurements fit to the model. Apart in this area where we are dominated by the cosmological errors. So you see, essentially this number here is the square of delta t over t. We can do the same game by crossing temperature and depolarization, and you see the same game, small errors up to 2000 in L, and in E, the same game, and apart from the quadrupole there, possibly affected by systematics, it's really amazing as a result. Here we show how well we have detected the lensing. We have detected the lensing to 40 sigma by using temperature and polarization, and with the precision of 9 sigma by using all the polarization. Numbers, the numbers that Gary was showing before, sorry. Numbers were, so apart from the numbers there, I would like to highlight the percentage, the small percentage of error with respect to sigma attached to each of the principal cosmological constants. For the first time, we were able to measure the reionization, reconciling this number with the astrophysical measurements. NS, it's measured with a very low error, 0.4, and this is discrepancy of the H naught, which Gary was talking about before. So essentially, we have detected, we have used the temperature polarization to give the best results at the moment on CMB, concerning CMB experiments. Conclusions. Let me go one by one. Planck has observed the ultimate cosmic variance limited primary temperature anisotropy, which means that whatever it will be done at IL will not be primary, will be dominated by astrophysical effects. We have a robust support to the standard 6 parameters lambda CDM, to the level of sub% error, tight constraints on possible deviation from the standard models, some hints on the anomalies. I didn't talk about the anomalies, but essentially the anomalies, let me go back a couple of slides. I'll show one anomaly which was seen by, yes, this is the one. This is an anomaly which has not a big statistical significance between 2 and 3 sigma. And so we have to look at that carefully. And come on. And what else? Tensions within the H naught measured with supernova and measured with CMB and PO. CMB lensing can be used at this point as a cosmological tool. And this is my view. The Planck cosmic pi, 5% of the energy content of the universe is something which we know, ordinary matter. The rest is totally unknown. What is that? That is dark energy, that is dark matter, and are we convinced that we have done everything? I'm not. So we need something more, probably new physics. Future experiments. They have to do what Planck did for the temperature, CMB polarization on isotopies. And there are a number of experiments on ground, in balloons, and in space. This is the wrong transparency, I had more. In space, there is one experiment planned by JAXA, the Japanese, which is planned to fly in 2027 with the goal to measure, to have a better measurement of the beam measurement, better sensitivity on the beam modes. So at this point, I think I have to thank you, and thank all on behalf of the Planck team, everybody who has worked on Planck. Thank you very much.
Thank you very much. Now I invite Peter Levi, head of the Wigner Institute, and Thomas German, scientific secretary of the board, to present the Gribov Medal.
Okay, it is a great pleasure on behalf of the EPS High Energy and Particle Physics Board to award the 2019 Gribov Medal for outstanding work of a young physicist in theoretical particle physics and field theory to Douglas Stanford, who has done pioneering work on quantum chaos and its relation to the near-horizon dynamics of black holes. And with this, I would like to ask Douglas Stanford to come up here.
Just one sentence. The Gribov Medal has been established in 2000 and first awarded in 2001. So this is the 10th Gribov Medal for young, talented theoretical physicists. And if you look into the list of the awarded in the last 10 years, you see that our recent nominee or awardee looking forward for a very bright career if he followed all of the fellow who got this prize. So, and I congratulate for you on behalf of the Eötvös Loránd Physical Society and Hungarian Academy of Science Wigner Research Center, where this prize has been established. Volodya Gribov was working in this institute in last 15 years. Congratulations.
Thank you. So now I ask Claudia Wortz to join me and to present the prize for young experimental physicists.
This year, we have the pleasure to award two young experimental physicists. And the first one is Josh Ben-David, and the second one is Lesia Szczucka. So Josh is awarded the prize for outstanding and innovative contributions to detector operations, software development, data analysis, and detector upgrades of the CMS experiment. And the prize is awarded also to Lesia Stutzka for outstanding contributions to experimental activities in particle physics, from the design and simulation of novel experiments, test beam operations and analysis, to data analysis and their final theoretical interpretations.
Thank you. And the last prize for outreach will be presented by Val Gibson.
So it gives me the greatest pleasure to present the 2019 Outreach Prize of the High Energy and Particle Physics Division of the EPS for outstanding outreach achievement connected with high energy physics and or particle astrophysics. And this year it is awarded to Rob Appleby, Chris Edmonds and Robin Watson for the Tactile Collider project that brings particle physics to the blind and visually impaired, especially school children, with using touch and sound. It's an incredible project, and I congratulate them most wholeheartedly.
All of the winners, please join for a common photo. Yes. One big picture, yes. Peter, Thomas, Val, Mauro, Claudia,
Okay, as there was a request or a suggestion to take a last group picture of the CDF and the 0 people in the room. So if all those members or former members of the 2 collaborations could come on stage or step forward for a one common group picture.
Okay. So I think that now we can start with our first plenary presentation. The speaker is here. Oliver, please. LHC status and future.
This is on? Okay. Well, good morning, everybody. First of all, I would like to thank the organizers for the invitation, for giving me a chance to talk about the LEC status and the future. So it's an honor for me, obviously talking for the whole of the accelerator sector here. First of all, for those of you not familiar with LEC, a very short overview of what the machine is about. So the LEC is a very big machine, 27 kilometers in circumference, wedged between the Lake Geneva, the Jura Mountains, and tangential to the CERN site right here, with the main experiments Atlas and CMS on opposite sides, and then the dedicated experiments LECB for flavor physics and Alice for ion physics, sharing the injections for the beam 1 and beam 2 in this machine. The machine is not only big in size, it's also big in terms of numbers. So each LEC dipole magnet weighs about 30 tons. We have about 1,200 of these dipole magnets in the machine. So we talk about a machine which has over 40,000 tons of magnets that need to be cooled down, such that the magnets become superconducting. For this, we use about 150 tons of helium, 90 tons at 1.9 Kelvin. We have over 1,500 power converters, over 9,000 magnetic elements, and over 1,000 beam position monitors, and over 4,000 beam loss monitors. I only play these numbers to highlight to you that in the end, I come back to this again and again, highlighting that reliability of the components and the systems for the LEC is a big challenge and one of the big tasks to achieve for the Halumi and the upgrade. In addition to the number of components, also the stored beam energy, I wanted to explore a little bit more on it later on. We have about 2,600 bunches with about 10 to the 11 protons per bunch in it. For the Halumi, we want to push this to 2.5, 10 to the 11 particles per bunch. That means we talk about 370 megajoules of stored energy in the LHC beams, and for Halumi, more than 700 megajoules for each beam in the Halumi machine. And for the magnets, we have at 6.5 Tesla more than 830 megajoules stored electromagnetic energy, and for operation at 7 TeV, we even exceed the 10 gigajoules in total. Now, I highlight these numbers because it's a big challenge for the machine, and I want to briefly highlight the energies, the management challenge of the LHC in the machine. So, bring these numbers in another context. So 10 gigajoules is the same as an Airbus 380 flying at 700 kilometers per hour, or the same as the stored energy or the kinetic energy of an aircraft carrier moving at 55 kilometers an hour, weighing 88 tons. And the stored energy in the beam, 700 megajoules, that's about the energy that you need to melt 1 ton of copper in the machine. So you have to be extremely careful with the machine and handlings. And also, if you want to get rid of the beam, you have to be very careful on the dissipated power. So 700 megajoules to be dissipated in less than 100 microseconds. You can calculate the watts. That corresponds to 8 terawatts of power that we put on the beam dump. That compared to the installed world electric capacity is almost twice of that we have installed in the world. Admittedly, you will do this only for a very brief amount of time, but nonetheless, your dump has to be sustainable and built in a way that it can cope with this. So the way out of this is for the stored electromagnetic energy is sectorizations. So instead of powering all the elements in series that it has been done in previous machines like the Tevatron and Hera, we power machines in different sectors. So we have for the LEC 8 individual sectors. So you translate the problem from 2 large electromagnetic energies on something that you can handle, but now you start to worry about tracking and reliability of individual sectors that you have to cope with in the machine. And for the beam dump, I mentioned this to you already, we have to have a very robust design for it. We have to have a robust core and window design. And in order to make this beam acceptable in the dump, we have to have dilution kickers. And again, you have to find the right balance between choosing many kicker elements to have more reliability in the systems, and then the likelihood of failure out of any of them going wrong at any time of the moment. So in the LHC, we worry about failure scenarios, local beam impacts, equipment damage. We worry about lifetime and loss spikes, distributed losses that could result in individual magnets to the loss of superconductivity, which we call a magnet quench, and therefore would have an impact on the machine efficiency. And in terms of the sectorizations, we worry about the tracking of the different 8 sectors in the machine together and overall reliability. And in order to highlight to you the challenge of reliability, I just want to comment on the cryogenic system. So we have 8 independent cryogenic arcs in the machine. If you want to have an overall availability of the system of 95%, that requires for each of the sectors to have 99% availability. So just highlighting to you that if you have a higher sectorization of the machine, that really pushes the challenges the machine in terms of reliability and system performance. So I'll start with a quick look back in the timeline of the LHC. So run one, we started with a famous incident highlighting the danger or the risk associated with stored electromagnetic energy in the machine. This was identified to the weak splices as a weak link in the machine. We then shut down the machine for 1 year to repair the sector 3-4, or for 2 years, from 2008 to 2010, and therefore reached a system with our DG at the time called as an unprecedented state of readiness to take data when we started the run one. However, we only repaired sector 3-4, so all the other sectors in the machine, the other 7 sectors in the machine still had weak splices. And in order to minimize or mitigate the risk for further incidents, we decided to operate the machine at the first run at lower energy, first at 3.5 TeV, and then after 1 year pushed it up to 4 TeV. And we operated the machine only with twice a bunch spacing with 50 nanoseconds instead of 25 nanoseconds, therefore halving the number of bunches in the machine. So that helped us to mitigate electron cloud effects, but had a challenge for the experiments, so the experiments had to cope with a higher pileup. But nonetheless, in the end, this was put the machine in a state that allowed us the Higgs discovery in 2012. This is not moving. There we go. Now, first long shutdown, 2014. This was a 1-year stop that we dedicated to the repair of all the links between the magnets, with the goal to come out of this and opening the machine for operation at nominal energy. The start at run 2, in the end, we found a second problem, a new problem that we hadn't foreseen, and I will show you a more detailed picture to that, as an electrical short to ground during hardware commissioning in the diode boxes. So again, this stopped us from moving the machine to the nominal energy and forced us to operate the machine at slightly low energy of 6.5 dG at the whole run 2. Now, the diode boxes, these are elements that protect the superconducting magnets in case of a quench in order to get rid of the electromagnetic energy stored in the magnet and to extract it and to dissipate it in a higher temperature. These diode boxes are located under each dipole magnet in a small metallic box, and this is a picture of the metallic box with the connectors that move up to the diodes. And any metallic debris that you have in the magnet, and this is unavoidable from the welding of the interconnections of the magnets and of the metallic structures, in the end gets collected in these boxes on the bottom. So this is a picture highlighting the dust, metallic debris that we have found in these diode boxes. Here's a magnetification of that, and here's an illustration that some of these metallic debris pieces can be rather large, a couple of millimeters big. And what we encountered during the startup of run 2 is that when we went through a training quench of the magnets, all of this is filled with liquid helium. And during a quench, the liquid helium gets briefly heated up, so you boil the whole system. That perturbs the metallic dust, moves it around in the diode box, and has a chance of leaving some of the debris and the interconnects of the cables that connect to the magnets and the metallic surrounding, creating short to ground for the magnet. So for this, we assessed that we need a systematic cleaning in order to mitigate this problem. And in order to avoid any risk associated with the short to grounds during the commissioning at the beginning of run 2, we decided to stay at a low energy of 6.5 TeV in order to minimize the number of training quenches that we need to bring the machines ready for operations. So again, for run 2, we limited the energy to an energy less than the nominal energy to 6.5 TeV. And now in long shutdown 2, we're addressing exactly this problem by mitigating this, by putting in better insulations in it and cleaning all the diode boxes in the machine. So run 2 operation, we had a machine which is well understood with margins for the magnets because we operated below the nominal energy. The optics was very well understood. We operated the machine with a global optics error of less than 10%, and at interaction points where it matters for the experiments to make the luminosity, we know the optics to better than 5%. We had very well established procedures and application software, so the operations was very efficient and well understood, and the magnet field errors was also well understood and well corrected. And that all paved the way for a very efficient machine operations in the machine. And to highlight that, I'll just give you a summary of the first run that we had. In run 1, we started with about 20% of the time, which was scheduled for operations in physics productions, actually in physics. The rest was then lost at fault times and turnaround times of just bringing the machine from an end of a fill to a new fill. At the end of the first of the run 1, we moved this up from the 20% to about 36.5% already. But then over the next runs, so run 2, we started already with 33% in stable beams, and towards the run, we pushed this consistently further up reaching almost 50% at the end of 2017. And if you look at the statistics of the last year of operations, so I took here the data from 2018 up to the first technical stop in June, we operate the machine with even over 50% efficiency. That means more than 50% of the time scheduled for physics, we actually dedicated for physics production. And that for a machine with that complexity is an enormous achievement. And in the end shows already that for the High Lumi project, we are, I think, in a good track that we can achieve similar performance levels in the future. In addition to the good efficiency of the machine, we also got a boost from the injector complex. And here one should highlight that the LHE is not a standalone machine. The LHE really lives and relies on the whole chain of injectors that we have at the CERN site. So for the proton operation, we have LINAC 2, then we have the booster. From the booster, we go to the proton synchron, PS, and from there into the SPS, and only from there we go into the LHC machine. So it's a whole chain that has to perform rather well. And in particular, the PS machine had a very interesting new production scheme for the protons in stock for the Run 2 operations, which we called the batch compression merging scheme. In order to illustrate that to you, on the bottom line, in the horizontal axis, you see the circumference of the PS machine expressed in times as one revolution time. You see that you get 8 bunches injected into the PS synchrotron. And on the vertical axis, you get the time as the acceleration goes on. And you see as the acceleration goes on, first of all, the distance between the bunches gets changed. So that's batch compression. So the batch gets compressed. And at top energy, the 2 bunches gets merged, and then they get split again into 3 bunches. So you translate the 8 bunches into 12 bunches with a very good brightness and with a very small bunch separations, exactly the 25 nanosecond bunch separations. It's a very elaborated scheme, which was only possible in the PS thanks to very good understanding of the machine and a very complex RF system, which has various RF frequency systems that can work hand in hand in the machine. All of that allowed us in Run 2 to operate the machines with about 30% higher brightness than was initially foreseen in the machine, and therefore boosted the performance reach of the machine. So we had a higher than nominal beam brightness in the machine. The performance in the end was limited by the number of events that the detectors could actually digest, so it's very good. We could push the detectors up to what they can actually take, and also by the cooling power in the machine, because we only had a limited amount of cooling in stock for the triplet magnets next to the interaction regions, and there we reached also the cooling power limit. The machine was designed for 10 to the 34, but we reached a performance level of 2 10 to the 34 in Run 2, and at that point we reached the limits of the detectors and the cooling capacity in the machine, essentially. So this is a track record of the machine over all the runs that we had, Run 1 and Run 2. Should highlight here that the first run in the first year of operations in Run 1, we had to magnify by a factor of 50 in order to make it even visible. It's a plot I took from the CMS page. And you see this very impressive increase of the performance over each of the years. And in the last year of operation, 2018, we almost reached 70 inverse femtobarn in 1 year of operations. It's a very impressive number. One should always keep in mind that before one goes into inflation of these numbers, that all the luminosity produced by all hadron colliders before the LHC was about 11 inverse femtobarn. So in 1 year, the LHC can deliver more than 5 or 6 times that in 1 year. So the integrated luminosity, Run 1 with lower energy was about 30 inverse femtobarn. Run 2, we produced a total of 160 inverse femtobarn with about 70 inverse femtobarn per year at hand. Combined, that gives you about 190 inverse femtobarn by the end of Run 2. And for the next run, after long shutdown 2, we have a goal of producing another 160 inverse femtobarn, so that the new goal for the LHC operations could be increased to 300 inverse femtobarns by the end of the LHC lifetime. And I should highlight here that the initial goal was about 300 inverse femtobarn. The next challenge that we encounter in the LHC after this is radiation level or radiation damage to the magnets. And in order to illustrate that to you, I have here a plot that has a distance from the interaction point. The magnets are not highlighted here, but this is the position of the first focusing quadrupole, the Q1, Q2, and these are the Q3 triplet magnets, and then you have the orbit correctors at this side. And on the vertical axis, you see the expected radiation dose once the machine has delivered 300 inverse femtobarns to the detectors, expressed in megagrays radiation. And you see that at the Q2 magnet, you expect at 300 inverse femtobarns about 27 megagray radiation. At the orbit correctors, about 20 megagrays of radiations, and the cold bore insulation will probably reach about 35 megagray of radiations. For those of you not familiar with these numbers, at about 10 megagray, you expect any epoxy or any insulation material to become brittle and not have mechanical structure anymore. And since we use epoxy materials for gluing the coils together, this is where we expect that the magnets will just lose mechanical integrity and have to be replaced by new magnets. So this requires a replacement of the triplet magnets by the end of run 2. This is also a highlight why we should not push the performance too much beyond the 300 inverse femtobarns, because then you run the risk of breaking the magnets without a scheduled intervention. And we have to replace them with a new system that is more radiation hard and opens the door for the high Lumi performance. For radiation hard, the only choice that you have there is to incorporate active shielding in the magnet design. So this is a cross-section of the cold bar of the magnet, the beam screen in the center. And for the high Lumi magnets, what we now plan is we want to have about 1.5 centimeter thick tungsten blocks inserted between the beam screen and the cold bore with bigger cooling capillaries to take the heat out at the lower temperatures before it goes to the 1.9 Kelvin of the magnets. And that most of the radiation actually gets absorbed in these tungsten blocks before the radiation can reach the coils of the magnets. And the whole design is done such that the radiation to the coils in the end will also reach about 20 megagray once we reach 3,000 inverse femtobarn of integrated luminosity in the machine. So this requires larger aperture magnets, and larger aperture magnets requires a new magnet technology. For the LHC, we have 70 millimeter diameter in the magnets and 210 Tesla meter gradient. For the high Lumi magnets, we go to 150 diameter, so more than twice the diameter of the existing magnets, reduce the gradient slightly to 170 Tesla per meter in order to be within reach of the available technology, requiring us to make the triplet magnet slightly longer. And therefore, we need magnets which now are capable of sustaining a peak field of 12 Tesla at the coils, and that requires new magnet technology, and we use niobium tin technology for the high Lumi magnets for this. Here one should highlight the development of niobium tin magnets is not a trivial affair, so it really took us a lot of time. We talk about a 15 to 25 year R&D program that was mainly driven by the high Lumi requirements, and we did this in close collaboration with our US colleagues and US lab. Where the high Lumi project with its gold pods really drove the R&D efforts to develop 11 to 15 Tesla magnet technology based on niobium tin technology. Just to show you that we think we're ready for this, so these are a couple of pictures. The second short magnet under preparation at CERN. This is already an older picture. We're now preparing the long magnet at CERN too. Here's long magnet preparations at LBNL in the USA, 4.2 meters long. And here examples of the infrastructure, an example of 1/2 of the magnet shell once the niobium tin coils are all wound and put together, glued together in the epoxy as one block. So I think we're ready. The magnets are ready to be tested and installed in a couple of years in the machine. With that, I think I addressed briefly the actual challenges or goals for the high Lumi project. So the main objectives of the high Lumi project are twofold. First of all, to extend the lifetime of the machine by another decade to allow operations beyond 2025 up to the mid-end 2030s, and to open the parameter space for operations that allows you to produce an integrated luminosity in excess of 3,000 inverse femtobarn for the experiments. This implies an integrated luminosity of about 200 inverse femtobarns each year. So that means a 4- or 5-fold increase with respect to what we have produced in the last run. And at the same time, the experiments don't want to have too much of anything at the given time. So this is an example I think I took from Atlas, what the tracks look like for 5 events in the detector and what it looks like when you have 400 events in the detector. And it's obvious from this, I think you don't want to have too many tracks at the same time if you still plan to do precision physics. So therefore, the experiments have asked us to make the configuration of the high Lumi LHC such that we do not have more than 140 events at any given bunch crossing at a time. And that translates to peak luminosity of 5×10 to the 34 for the machine. And we also devised ultimate parameters where we push this slightly higher up to higher values. But it's clear that these two requirements are counterintuitive. So on the one hand, you want to have as much as possible in a given year, but never too much at a given moment of time. So the only way out of that, or to cope with that, is operation scenarios where you operate the machine with a leveled luminosity, and you really work on the machine to maximize the machine reliability and efficiency of the machine. So these are the key design ingredients for the high Lumi project. For the leveling, in the LHC, we have 3 essential leveling mechanisms at hand, and they're listed here vertically with increasing complexity, and I will comment on why this becomes more complex as you go down. The first one is just to separate the beams transversely as they collide with each other. Gives you a small offset that reduces the luminosity. We can change the crossing angle with which the bunches collide at the action points, and we can change dynamically the beam size at the collision point by changing the optics functions in the action points. This becomes more complex because beta star or the beam size variations means that you couple all the previous systems together, and you couple that because we have to operate the machine with a crossing angle. And to illustrate that to you, here's a schematic picture of the interaction point in the LHC with the interaction point in the center, the triplet focusing magnets here, and then you have a separation recombination dipole magnets which bring the two proton beams from the separate apertures and the arcs onto one common trajectory in the experiments. All of this is about 130 meters long between the D1 magnets on both sides, so 150 meters. For high Lumi will be even slightly longer. And we have 50 meters in between the triplet magnets. And we operate the machine with about 2,800 bunches with 25 nanosecond spacing. That means in this drift area, or the region where the two beams share a common beam pipe, you have approximately 30 unwanted collisions per interaction point. And that requires, in order to make sure that the beams only collide at one point and not in all of 30 of them, you have to operate the machine with a crossing angle. And you have to make the crossing angle big enough so that the nonlinear force that the bunches see and the parasitic intercrossings become small enough in order not to perturb the beam during operations. So you want to have a separation at these locations between 12 and 10 sigma. And that means the crossing angle that you have to provide during operation depends actually on the beam size at the interaction point or on the beta star value that you have. And this fact, that makes the operations with the dynamic, or the leveling with the dynamic beta star so challenging. As you change dynamically beta star during operations, you inadvertently also affect the crossing angle, you inadvertently affect the separations of the beams. In order to have a good control of that, you have to work yourself progressively from the easier to the more difficult levels of the leveling options that you have. The experience of previous machines, like RIC or the Hera machine, they have shown that the beam lifetime in a hadron collider is very, very sensitive to transverse profile matching and the overlap of the colliding beams. So we were in the beginning very much worried about this. In the LHC, it turned out that we, I think, master actually all of them by now. So this is an example of the separation by, or the leveling by parallel separation. This is something now we actually use already routinely for the Atlas and the LHCb experiments. As the bunches go in opposite directions, you shift their transverse position slightly. Here on this plot, you see versus time the luminosity that you expect, and here you see them for fields where we don't have this leveling put in place, and then in the orange color, you see the whole performance and operations with this leveling being put in place. And you see that we level the luminosity quite nicely, and what is nice from this experiment, or from this experience too, is that the experiments were happy with the conditions as well. So this is something that works in the LHC. And even the dynamic beta star adjustments that has been tested in machine development studies in the LHC already. So during 2018 operations, again, horizontal axis, you see time, and here you see the luminosity. And you see here the beam size, or in magenta, you see the beta functions at the interaction points. And then in blue and in black, you see the luminosities measured in 0.1 and 0.5. And you see that we are capable over a time of about 5-6 hours to move the optic functions up and down, and that the luminosity actually tracks nicely the change of the optics function. So again, it's something we have in our hands and under control, and we can still keep the beams in collision with an accuracy of about 2 micrometers. That's very nice. So I think leveling tools we have at hand. And if you then want to operate and maximize the performance of a machine with leveling, what you do is you design for the highest possible virtual luminosity in your machine that you could dream of, and then you artificially reduce it lower for a given amount of time. So your operating scenario luminosity versus time looks like something like this, where you have flat time of operations, where you just linearly increase the luminosity, you let it decay for a short time, just to maximize the luminosity harvesting for a given run, and then you have a turnaround time where you get rid of the old beam, fill the new film, accelerate it, and you start all over again. And one of the key factors in this is that the lifetime that you have in such an operation scenario is directly proportional to the total number of protons you have in your machine. So if you want to optimize the run lengths in such a scenario, you have to aim for the maximum number of protons in your machine. And of course, you have to maximize the machine efficiency, because any interrupted run that you have before the flat top operation has been terminated is an inefficient run by definition. So we want to have maximum number of protons and the highest efficiency in the machine for high Lumi. And for the maximum number of protons, we benefit from a second project that is currently being installed in the injector complex. It's LIU, the LHC Injector Complex Upgrade Project. I highlighted to you already that the LHC is not a standalone machine. So we have the LINAC 2 and the LINAC 3 machines, and the boosters and the Libre machine. And the proton upgrade project for the LIU has the goal of increasing the proton beam brightness to the maximum. So for this, we work on a new LINAC 4, which is a replacement of the old LINAC. So we go to H- injections. We increase the energy to 160 MeV now, and we have an injection current of about 40 milliamps for run and for nominal in target. And for run 3, we aim at about 25 milliamps operation target. For the booster, we increase injection energies. We also increase extraction energies. We have a new RF feedback system. We have new power converters, which are now solid-state power converters, so the whole machine undergoes a quite substantial upgrade. Also in the PS machine, we have a new 2 GeV injection, so higher energy, and a new RF system for better feedback system in the machine. And for the SPS, we have an upgrade of the RF power in order to cope with more protons in the machine, a new beam dump system, and overall campaign to reduce the longitudinal impedance in the machine in order to be ready to take on more protons in the machine. This is the timeline. We are right here in the middle of long shutdown 2, or for the LIU project, we're about the middle through it. For the LHC work, we are just a quarter of the work through in the upgrade work. Run 3 for ions, one should highlight, starts already in 2021. The LIU project also aims at an upgrade of the ion operation project by implementing slip stacking in the SPS, so bringing the bunch separations for the ion operations down and allowing us an increase in the luminosity. And in the LHC side, we introduce new absorbers and collimators in order to protect the machine against these higher ion beams. So run 3 will start in 2021 to 23, operation with 25 nanoseconds, hopefully at nominal energy now. The beam energy that we will start with, though, that is still under debate, and I think the directorate and the sectors, they will have a meeting with the experiments in November 2019 to settle whether we start again with the same energy of run 2 in the beginning in order to minimize the time required for the magnet training so that we have some time for physics generation in the first year of operations, or whether one moves right away to the 7 TeV. And the total production aim for the LHC now has been moved, or it's well in place to produce between 300 and 400 inverse femtobarn. Just a little bit about the timeline where we are in long shutdown 2. The main projects during long shutdown 2 is the LIU project. So this is highlighted here. For the LHC side, the main projects are installation work for the HiLumi project already, collimators and some protection devices, and what we call the DISMARC. This is a diode installations and superconducting magnets consolidation work that I mentioned to you before. And so far, we're dominated by this, I mentioned to you, and we are on good track. So far, so good. I think we are still on track to stay within the schedule that we have given us. This is a slide I took from Frederick Brory from the SPC meeting in June. You can also continuously observe this on the LHC dashboard, the progress that we have. But so far, I think the main message is we are on track. We still think we can manage it, and hopefully we'll finish long shutdown 2 successfully with everything in place. So I finish off with a couple of words on the optimizations of the performance for the HiLumi project. So this is a luminosity formula again. What you want to do to maximize the luminosity, so first of all, maximize the bunch intensities because that enters quadratically, and minimize the beam emittance, and that is done by the injector complex upgrade, LIU, as I mentioned to you. Then you want to maximize the number of the beam size, the constant power, that's the beta star or the triplet aperture. You want to maximize the number of bunches where you worry about the beam power and the radiation. I mentioned that to you. And the last resort that you have is this geometric reduction factor F. And I will highlight that or explain this a little bit more detail in the following transparencies. And for that, for the HiLumi, we plan on installing crab cavities in the machine and otherwise overall work on the machine efficiency by minimizing the number of unscheduled beam aborts and minimize the intervention time whenever something does go wrong in the machine. And I will comment on this very briefly. So that's the main goals for the LHC. So operation with crossing angle. And this is a graphical picture of this geometric reduction factor as a function of beta star. I highlighted to you that if you make beta star smaller, you have to increase the crossing angle. And if you have a crossing angle, then your effective luminosity gets reduced by 2 effects. First of all, the effective cross-section gets increased due to the tilt of the bunch ellipsoids, and the luminous region gets reduced because the bunches no longer fully penetrate each other. And this is where we started operations at the beginning of run 1. The geometric reduction factor was about 0.8. This is the design value of the LHC, so we designed it for a beta function of 0.5 meter. So we designed the machine such that you were ready to lose about 20% of the luminosity due to this effect. HiLumi LHC wants to push this to 10 to 15 centimeters beta star, so below 20 centimeters. And if you don't do anything about this, that means you lose about over 70% of the potential luminosity in your machine just ineffectively even though you maximize the proton intensity. And again, that translates in a rather inefficient operation mode for the machine. The way out for that is that you tilt the bunches longitudinally, so you give a kick to the head and to the tail of the bunch in opposite directions so that it tilts longitudinally, and in such a way that as the bunches go along the crossing angle at the interaction point, they effectively overlap again fully, have an effective head-on collisions in the machine, and that reduces the metric reduction factor. For a proton machine, this is a novelty, so we worry about sizes of these elements that we have to put in and the noise that it puts onto the machine, and because we have challenging space constraints. And for the LHC, we developed a novel design of these cavities, again, in a collaborative way together with our UK and the US partners. And in the end, we settled on two designs, one for a horizontal deflection and one for vertical deflection, called AF dipole and a double quarter wave AF cavities. This is a prototype that we've built and we installed in the SPS. And in the present baseline, we aim at 4 cavities per interaction point per site. So we talk about a system with a total of about 16 cavities in the High-Lumi area. Just a couple of pictures. So this is what the cavities look like during productions at CERN in the clean room. So this is double quarter wave machine. This is the preparations of the tuners and couplers. This is how it all put together. We have 2 cavities and 1 cryo module being assembled here also at CERN before installation in the SPS. This is the whole assembly being put into a bunker in SM18, our test facilities, where we test the cavities before they get installed in the SPS. And these are then first results that we had in 2018, where we actually measured in the SPS for the first time the effect of crab cavities on a proton beam. On the left, you see the result when the crab cavities are tuned to 0 voltage. On the right, when you see that the voltage in the cavities get turned on, and you see exactly the effect that we hope for, that the bunches longitudinally get tilted. So again, we think that this technology is ready for the High-Lumi, and it's ready for production and installation in the machine. Cleaning efficiency, I highlighted to you too, and reliability of the machine. So I want to briefly comment on the collimation system upgrades that we have in the LHC. So this is a schematic picture around the machine with all interaction points, CMS and Atlas on top and bottom, Alice and LECB on the side. And then we have the cleaning areas in IP3 and IP7, where we have dedicated collimators to get rid of any protons that run stray from the beam core and have a risk of being deposited in superconducting magnets. So we have over 100 kilometers in absorbers to protect the superconducting magnets in the machine. And so we replace at the interaction regions complete new layouts with normal materials for IR1 and IR5. We have 4 tertiary collimators there and 3 physics debris collimators. We have new collimators in the dispersion suppressors of IR7 to cope with the losses primarily from the ion operations in the machine. Then we will replace one of the nominal superconducting LHC dipole magnets by 2 new shorter 11 Tesla magnets to gain the space for an additional collimator to be installed in the dispersion suppressor of the cleaning insertions. We have dedicated collimators foreseen for High-Lumi in the Alice areas in order to absorb debris coming out of the induction point from Alice. And we have new low impedance, high robustness secondary collimators in the main cleaning insertions in order to lower the impedance of the machine and therefore opening the door for operations with high proton intensities in the machine. In total, we talk about 56 new collimators to be produced by Long Shutdown 3, and which are in the current baseline of the High-Lumi project. Just a couple of pictures. So this is the first prototype, long prototype for the 11 Tesla dipole that we are installing in the dispersion suppressor of IR7. Longitudinal picture of that. And again, I think we're ready there and on track for installation during Long Shutdown 2 already. In terms of reliability and minimizing the time for interventions in the LHC, so we also work on new underground areas in the LHC. So we need space for the new High-Lumi equipment, for example, cryogenic systems, new power converters. We need to upgrade the cryogenics for the triplet magnets next to the main experiments if they're supposed to run at high luminosity. We want to remove all active components from the tunnel area in order to minimize the radiation to electronics and therefore induce the fault times. And we want to have a new installations where we allow continuous access in the machine, even when the machine is still closed, so that people can maintain and work on the equipment in the machine. So for this, we're building a new access shaft, we're building a new underground cavern and a new gallery and connection galleries to the LHC in the 2 main experiments, Atlas and CMS. And then we call this a double-decker solution because the new tunnel is slightly above the old tunnel, and then we connect to the old existing tunnel via vertical cores, which make the connections from the new infrastructure to the old infrastructure. This is a more detailed picture of the new cavern that we have there with power converters here in this parallel gallery. And then you see here the connections to the machine, or the old machine, the old tunnel. And also for that, we worked on a new powering scheme for this machine where we developed a new high-temperature superconducting link for the cold powering. So we no longer have water-cooled copper cables coming from the power converters to the magnets, which needed rather short distances in order to be efficient. Now we have a superconducting link, which allows you to transport the current efficiently over long distances of up to 100 meters, which will power all the new components in the machine. Because we're worried about the effect of civil engineering on the operations of the machine. So for run 3, we cannot operate or do the excavation work during run 3. Therefore, we decided to advance all the civil engineering work when the LHC is not operating. That's the main reason why we advance as much as possible the civil engineering now during a long shutdown 2. So we're excavating everything during long shutdown 2, so that during the run period, run 3, we're left with the low impact work in the tunnel, which means installation of the infrastructures, installations of new components in the tunnel. There's a couple of pictures. So there's one picture from April in point 5, panoramic view, where you start at the bottom shaft of the bottom of the shaft, and then the first start of the alcoves, which is excavated here left and right, and it's a panoramic view. You have the same picture from June this year, and point 1, where you see we're a little bit more advanced in point 1, where we have done all the concrete sealing already in the tunnels, and we start the drilling of the transverse gallery already in the tunnel. Okay, so I think I'm coming to the end of our presentation. So beyond high-lume LHC, after 31, we start with long shutdown 4. So you have various items there on the agenda. We looked at the full energy exploitation of the LHC. That's a study where we looked at, is it possible to actually push the energy beyond the 7 TeV to 7.5 TeV? So far, we have not found any showstoppers, but it's also not a very appealing proposal so far. I mean, we discussed with the experiments, and the experiments gave us a feedback is that they would be interested in an increase to 7.5 TeV if you don't lose more than 20% in integrated luminosity whilst you do that. And I think the studies that we completed so far shows that you expect to lose about 20 to 25% in integrated luminosity just because you have less margins and because the machine efficiency will go down. So whether this in the end is really attractive needs to be seen, and we still have to fold in how the new components for high-lume actually will perform at these higher energies. We have the options of transforming the LHC into an electron-proton collider with LHEC, and beyond 2037, I think the only option you have at the hand is new proposals. So we discussed the high-energy LHC, but I think recent experience with the magnet development again puts us more or less in questions, because pushing the magnets to 16 Tesla or beyond is very, very challenging. So, and I think this would only make sense for magnets beyond 16 Tesla, or then all the projects that have been discussed in the European strategy meeting that we had in Brussels just a couple of weeks ago, but I think I leave that to somebody else to comment on. And then I'm done with that. Thank you.
Thank you, Olivier. We have time for 2-3 questions, if any. Please, Dimitri.
You mentioned about the radiation doses at the triplets, yes, so which are very high. Your plot, is that for the really measured doses, or it's some calculations? Yeah.
It's a combination of both. So we continuously measure the radiation, and then we try to make a model which fits the measured radiation with luminosity and total beam intensity being put in the machine. And out of that, you then make the projections what you expect in the end.
So you understand them pretty well,
yes.
So you can predict. Yes. Very good.
Any other question, comment?
Okay. Hi. I really like the proposal of you tilting the bunches in 2 different directions. I see in one of the bunches you have bunches tilted in 2 different directions. Is it a lot of work? Because tilting in 2 directions might be having play around with a lot of magnets. So.
Well, we have the system is totally local, so the crab cavities are around each of the interaction points. And we tilt the magnets or the bunches only as they go through the experiments. And once they go back through the machine, they're perfectly aligned again to the nominal design orientation. So this is a local deflection we do only in the action points.
It doesn't affect the stability of the beam, right?
Well, we hope not. So that was one of the big worries that we had. So that's why we insisted that we have to test the system first in the SPS. And all the tests in the SPS were very positive. That worked fine. So from that, we take a lot of confidence out of it that in the end it should work. One should maybe highlight that as a plan B, all of the upgrade ingredients for the high-lume project are all small ingredients which all add up. So I think if you don't have the prep cavities, you will lose maybe 20% of your total reach. And the system is designed such, and we tested it in the SPS already, that if there are problems, you can turn it off and still operate. So you don't jeopardize any of the future runs if there are problems with the system. But if it works, it gives you the additional boost of 20% higher performance reach in the machine.
Okay, thank you.
Okay, any other? I don't see, so thank you, Oliver, again. It's time for coffee break.